Dear NEET aspirant, today we see the J.J. Thomson model as well as Rutherford atomic model. This J.J. Thomson model, it's a first proposed the detailed model of atom. Okay, he is a first proposed the atomic model. Especially there is a detailed atomic model. This the next it's confirmed in the atom. It's atom. It's a spherical shape. This atom is consisting the uniform the positive charge as well as negative, like that they have proposed. The charge as a uniform spread over the entire atom. Okay, as well as the mass of atom. There is a mass is equal to entire atomic mass. Entire atomic mass. This mass is the overall the spread out that positive and negative charge in the entire atom. So that's why the mass is considered as a whole atom. Okay. So the next there is a this model is similar like of that. There is a plum budding. Okay. There is a plum budding model or watermelon model. Okay. There is a watermelon model. This plum budding model or there is a watermelon model. Okay, for example, see this is an atom or I drawn here. See, this is an atom. This atom it consisting there is a negative electron, negative charge, and that empty space is considered as a positive charge, and this considered as a negative charge. Okay, so the electrons as well as proton, the positive and negative charges is spread over the entire atom, like that the J.J. Thomson model is proposed. Okay, so for this time also the experiment that much level is not developed. Okay, so it's a main drawback. It's a drawback, actually drawbacks. There is a the atom it cannot spread over the entire mass. Okay, entire atom that is mass is considered evenly spread over that atom, cannot be over that atom. Okay, so mass is cannot overall or over all atoms. Okay, the next it's just as a static model. Okay, static model. It does not reflect the movement of electrons, so that's why there's a static model, and it could not explain the alpha particle experiment. Alpha particle experiment. This could not explain this alpha particle explanation. Actually, this alpha particle explanation is given in the Rutherford atomic model. Let's see the Rutherford atomic model. This model is also called alpha particle experiment. Alpha particle experiment. Okay, okay. So he taken as the gold foil, gold plate. Okay, this gold foil, and this backside is a screen. This covered or is coated as a zinc sulfide, as well as the lid is there. This lid is a monochromatized for upcoming alpha particle. That's why is used. This lid is there. Here we passed the alpha particle. This alpha particle this fall on here. So some alpha particle are moved to the straight line. Then some alpha particle is scattered in this way. Okay, and some alpha particle is scattered in this way, and some alpha particle is return come back, and some alpha particle is scattered in this way. Okay, from this experiment actual this is alpha ray. Okay, alpha ray, we know that alpha ray it's a positive ray. Okay, so this midpoint the atom is there. In that atom we can clear a diagram drawing here. This is a nucleus. Okay, this is a nucleus. It's a positive charge. It's a positive charge. The alpha particle is passed in that way. There is no deflection. Okay, here is no deflection, but in the case of the center of that nucleus, they have deflecting. So from like that reason that the central part of that atom, the alpha particle is made, they have deflected. So this concluded that the Rutherford, the central part is consisting as a positive charge. Okay, positive charged particle, like that. Okay, so here the most of the alpha particles went straight through the metal foil undeflected. It means that there must be very large empty space within the atom. Since few of the alpha particles were deflected from their original path through the moderate angle, it was concluded that whole of the positive charge is concentrated, and the space occupied by this positive charge by this small space of entire atom. The positively charged heavy mass which occupies only a small volume of the atom is called as a nucleus. Okay, so the nucleus as proposed in the Rutherford, this nucleus is possessed as a positive charge. Okay, the next the very few some alpha particles suffered strong deflection. See this alpha particles are strong deflection because this nucleus is a positive charge, as well as for upcoming alpha particle also is a positive charge. The positive as a reflected. So for that reason, that a few alpha particles are strong deflection. Okay. So on the basis of this scattering experiment, Rutherford proposed the model of the atom that is called nothing but there is a nuclear atomic model. Okay, there is nuclear atomic model. Nuclear atomic model. Okay, because he is proposed that nucleus as a central part of that atom. Okay, the next that is, for example, see in the case of atomic volume or atomic radius, atomic radii, there is 10 to the power of minus 8 centimeter, as well as the nucleus radii 10 to the power of minus 13 centimeter. So we can go to that ratio between the nuclear radius as well as atomic radius. See, in the case of Ra as a atomic radius divided by Rn as a nuclear radius. So atomic radius, what is the value? We know that 10 to the power of minus 8, and the nuclear radius 10 to the power of minus 13. So this inverted, we can get that as Ra divided by Rn, that is 10 to the power of 5, 10 to the power of 5 times. So that's why the atomic radius is equal to, there is an atomic radius equal to 10 to the power of 5 times of the nuclear radius. Okay, so this is a very very important. The atomic radius is equal to 10 to the power of 5 times of that nuclear radius. So the atomic radius is directly proportional to cube root of the entire mass or nucleons. Cube root of the nucleons. That is nothing but mass number. So we can introduce that as some constant value. So that's why here R is equal to R naught and a power of 1 by 3 centimeter. Okay, here this R naught as a constant value, that is 1.33 into 10 to the power of minus 13. And so for that value we can go to substitute here. So here R is equal to 1.33 into 10 to the power of minus 13 into a power 1 by 3, that is a centimeter. Okay, okay, so this formula is a very very important for calculating that the radius of atom. Okay, the next the volume, we know that a cube or r cube. Okay, so for that reason the volume of atom divided by volume of nucleus. Okay, so volume of atom, actual atomic radius, that is a Ra cube divided by Rn cube. So what is that Ra? There is a Ra cube divided by Rn cube, that is equal to, there is 10 to the power of minus 8 cube divided by 10 to the power of minus 13 cube. So we can go to solve this, we can get in that 10 to the power of 15. Okay, so the atomic volume as well as nucleus volume, the ratio between these two, we can get it the 10 to the power of 15. Okay, okay, so this the empty space around that nucleus, that is occupied the electrons. Okay, then the volume of atom is about 10 to the power of 15 times of volume than the nucleus. So that's why the Ra of a cube is equal to 10 to the power of 15 Rn of that is a 3. So the volume of that atom, that is equal to 10 to the power of 50 times of the volume of the nucleus. Okay, so that's why the majority of the empty part that is presented in that atom, but the central part that's called nucleus, that nucleus is presented as a proton as well as neutron. So this model is similar to that solar system, the nucleus representing the sun and revolving the electrons as planets. Okay, next there is a drawbacks of that this model. Actually, according to that Maxwell, according to Maxwell, the every work is loss of that some energy. Okay, the energy is lost. So the electrons are revolving around the nucleus. For that reason, they have energy loss out for sometimes in the sudden case it goes to that fall on that nucleus. So if like that the electrons or atom is presented, that atom is destroyed, because the electrostatic force as well as the coulombic force, they have equal, then only that atom is more stable. Okay, so this is not explained in that Rutherford. And also that the energy is lost out, that is continuously, but not in the continuous, there is not continuous spectra, not continuous spectrum. That's why the energy cannot be continuously lost out. There is a packet or the small bundle like that, the energy is lost out. So that's why that is the drawback of a second if the electrons lost energy continuously, the observed spectrum should be continuous. So but the actual observed spectrum could not, there is a continuous. So that is why there is a loss of energy by electrons not continuous in an atom. So the last one, it's the energy cannot be say anything. So it's a nothing about distribution of electrons around the nucleus and the energy of these electrons. So energy is not explained. Okay. So these three are the drawbacks of that Rutherford model. Anyway, that in this video we learn that is a J.J. Thomson model, that's a watermelon-like model, and Rutherford model. Okay. Okay. Thank you. Thank you to all. If you like it in this video, you can subscribe and share your friends. Thank you. Thank you to all.